This idea of projection and try to get acquainted with the notation, the variables and things like that that they use. So it says here, given a vector y in a subspace W of R, there's a vector y hat in W such that one, y hat is a unique vector for which y minus y hat is orthogonal to W, whatever that means. And number two, y hat is a unique vector where it's on W, but it's the closest vector to y. Okay, so these are the two ideas that we're going to get out of today. And then hopefully extend it to the next section, 6.4, where we're going to construct this. Let me throw out some formulas, maybe do an example or two, and then have you guys try to visualize this with some volunteers who want to act like vectors.
I am pro at being a vector.
Okay.
I'm an actor. So.
You're totally a vector.
Right?
Vector relations.
But do you have direction and magnitude?
Oh. You gotta mess it up.
So, our first theorem has kind of like a construction, but also a way for us to find the components and the ideas. And it falls under this thing, theorem. So suppose W is a subspace of Rn, and Y is in Rn. That may be in W, but maybe not in W. And that means this can be written uniquely in the form Y is equal to Y hat plus Z, where Y hat is that vector that we talked about in the previous paragraph here. Y hat is in W, and then Z is this new vector that we're going to create that's perpendicular to W. And we could be in Rn, but we're going to try to do an example. I'm going to do an example in R4 first, and then we're going to try to construct our example in R3, where we can actually visualize it, because R4 you can't visualize it. But we'll go through the computations in an example in R4 first. So y hat is this new vector now that's supposed to be in W. And what we want to do is we want to use y and those components in W. Now W is a subspace that's spanned by U1, U2, and U3, etc. So it's a subspace that already exists and is spanned by those. And then we use those vectors, U1, U2, U3, we use all those vectors in W to create y hat. Okay? So let's do a quick example. Where's my example? Oh, by the way, we already know, but just in case, y hat is the orthogonal projection of y onto W. Now, we had orthogonal projections onto a vector and maybe even onto a line, but now we're talking about a general space. So let's add that on in our notes. And if we're just talking about projecting onto one vector, then we're kind of at this formula which we learned last time. But now we're going to extend it to more. Okay? All right, so our example. Let's say we wanted to, we're in R4, can't visualize this, so we're in R4. Let's say that U1, U2, U3, and U4 are a basis for R4, which means they're linearly independent, and they also happen to be orthogonal. So that is a special scenario where you actually have an orthogonal set. So just looking at U1, U2, U3, and U4, if you take a look at any pair of them and dot them, you'll get 0. You want to just do that in your head real quick? You don't have to do all the pairs, but okay. So now that you're convinced of that, it says here we want to write V as a sum of two vectors. One of them is a span of U1, and then the other one is a span of the other three vectors. So, according to this, my pen. So according to this formula, my pen doesn't work now. So according to this formula, the formula that I just did over here, I want to express a new vector that's going to project onto this four-dimensional space. So we'll call this is V, so we'll call it V hat is equal to, and according to this, I need to take the dot product of my vector with each of those basis vectors, and then divide by the dot product of the basis vector with itself, and then multiply it by the basis vector. All right, so let me just write down the formula. This is V dot U1 over U1 dot U1, and then multiply that times U1. So these are all vectors. I'm not going to draw those little arrows anymore. Plus V U2 over U2 dotted with U2 multiply with U2. So the dot products are dot products, and then when you have this extra vector attached over here, it's a scalar multiplication, because the fraction over there actually is a scalar. V dot U3, U3 dotted with U3 times U3 plus V dot U4, V U4 dotted with U4, multiply with U4. So this is what we have. Now, we want one of them in the span of U1, and then the other one in the span of the other three. So after we find these vectors, we're just going to write them as one vector. But I think the better exercise is to try to figure out what these vectors are. Okay, so let's do the dot products. I'm just going to see if I can just come up with these constants. So V dotted with U1, so that's a 4 plus 10, that's 14. 14 minus 3 is 11, plus 3 is 14 again. So if I make any mistakes, you guys can just correct me. U dot U is 1, plus 4 is 5, 6, 7. And then multiply that times U1. Okay? Is that part clear, that idea? All right, now V dotted with U2. So that's a -8.
6. It's 9.
It's 9? Okay.
Correctly memorized.
Well, I'll trust you. And then U dotted with itself is 4, 5, 6, 7. 7 again. So 9 sevenths this time. times u2, which is minus 2, 1, minus 1, 1. V dot u3, that's 4 plus 5 is 9. 9 plus 6 is 15. 15 minus 3 is 12. And then u3 dotted with itself, 1, 2, 3, plus 4, 7 again.
Is there a reason you wrote 14 over 7 instead of 2?
Well, I just did it. I just did the numerator and denominator. We could simplify it to 2. And then the last one, negative 4 plus 5 is positive 1. 1 minus 3 is negative 2. Negative 2 minus 6 is negative 8. And then it looks like this is going to be 7 again. Does that look okay? Yes.
I think is U2 the second one instead of 9. I think it's 3. Yeah. Yeah. Oh.
Okay. Thanks, Randall. All right. We good? So, I think we could be done at this point, but according to them, they want it written into two vectors. One of them is this vector over here. This is just 2 times this vector. So that's 2, 4, 2, 2. And then plus this vector over here. So, I don't know. You do that, I guess. Can you do that in your head, or?
So you're
Just multiply each of them and then add them all up.
okay.
How would you do that on that one?
You can, go on. I'm just going to put star here and just say we're done. All right? So that's the idea behind doing these problems, or in using this formula. All right? So I do want to get at, and if you don't understand this, we'll hopefully get a visual of this. What y hat is, what z is, what y is, and what u1, u2, u3, etc. are. And so we're going to do a simple example in 3 dimensions. But before we do that, let's keep going with some more stuff. Some more theory first, and then we'll see if we can get the relationships going. So. This is a property of a orthogonal projection. So if U1 and if you have a set U1 through UP, and then you have an orthogonal basis of W, and Y happens to be in W, then the formula of the projection is going to be the same representation as Y. That's to say that the projection of Y onto W is equal to W. Now, the projection of Y onto W is going to be equal to Y if Y is actually on W. So think about that. Think about projecting if this is Y and this is Y itself, and you want to project it onto Y, and then it's kind of boring. Then a projection of Y onto Y is itself. Get it? Yeah, sure. All right. The other part of this says that if you project y onto w, then you're going to get y hat. And y hat is on w. Okay? Yes?
So the dot product of y hat and y is 0, right? Because it's an orthogonal projection.
No.
No. Okay. Is y hat and w 0 then? What is y hat orthogonal to?
Y hat is not orthogonal to anything. Y hat is on w.
Okay.
All right?
It's y's projection onto w.
It's y's projection onto w.
Okay.
Yes.
All right.
That's what my head is.
Okay.
That was an orthogonal.
All right. So what this is saying is that y hat is an orthogonal projection of y onto w. So y hat is on w, and then y hat is going to be the closest, the best approximation of y if you're just restricted to being in w. Those are all just, I don't know if that makes sense. Okay. Oh, and then the other neat thing is that we're talking about these things as orthogonal projections. So if they're orthogonal, then these formulas work. The theorem works for us. If it's not orthogonal, then we have to find a way to make it orthogonal. So if they are orthogonal, though, then the theorem works. And then this last theorem over here tells us that if they're more than orthogonal, if they are actually orthonormal, remember what orthonormal is? It's orthogonal and it's a unit vector. So not just that they're perpendicular, but they're also unit vectors. So if they're also unit vectors, then your new formula becomes this. And why does that make sense? That makes sense because the original formula looks like this. And imagine if U1, U2, U3, all the way up to UP, imagine if they were all unit vectors. What are the denominators going to be?
Bunch of ones.
They're just going to be ones, the magnitude, which is 1. So if they are orthogonal, then your formula becomes orthonormal. Then your formula becomes a lot simpler. Okay? All right, so I don't know if you guys have a visual of this, but let's see if we can visualize it. So I'm going to need a vector U1. Okay, let's stand over there next to that whiteboard. I need a vector
Get in line.
U2.
Stand for race, right? U1, U2.
Okay, so
Happy hashtag U2.
why don't you guys connect at the tails? U1 and U2.
Dijo que peguen las colas.
Now, if they are not orthogonal yet,
Let's get it.
are you guys connected? Connect.
Like that.
You have the video.
Connect your
Yeah, let me turn it. Probably
Facebook.
They'll just move.
Oh, by the way, it's not going to capture the screen because the exposure is not right. You're not going to see anything written. It's like
Now you tell me this?
What happened?
Nothing is fine.
It's been like 20 minutes, dude. You could have told me this like 20 minutes ago.
That doesn't help anything. There's no way to set the exposure properly.
Alright, just hold that. Hold that.
Is that your
Alright,
notes?
I got my new job. It's good, yeah. It's been. Well, I don't know what he's talking about the screen now, but.
I
don't need the screen.
technical.
Let's walk closer to that whiteboard.
You're an engineering major.
Right stuff.
Oh.
You
Now
know
I've-
the word technical?
Like having someone record
This
it.
doesn't
Yes.
look like that.
It's
You
recording.
have weird writing.
You got a cameraman over here.
You want to record this?
Hey, cameramans can be laughing.
Saludos a la
You
familia.
gotta be stable.
All right, who's U1?
You.
All right, Matt is
Well,
U1.
both of you.
Okay,
Different you.
If I said you,
so
then they're gonna think they won something.
let's figure out what the projection of U1 onto U2 is. So projection of U1 onto U2. So can somebody, don't have a smaller ruler. All right, I need Matt to be on the bottom, and then, well, leave it like that. What's the projection of U1 onto U2? Can somebody go over there and point and show me where it is?
Ish.
Yeah,
Wait,
where the shadow is.
U1
Right where the
onto
shadow is.
U2. So who's U1?
Get a flashlight, put it right behind
Okay.
it.
So projection of U1 on, yeah, if we had a flashlight, that would be nice.
I got you right here, dude.
Oh, here.
I don't have the stick.
Flashlight.
Oh.
Got it.
I get the big stick.
Someone order for a flashlight. There it is. That's it right there.
That's it, right?
Should be.
So that's a
little bit
projection
less.
of
Just
U1
a little
onto
bit less.
U2. This is Alan.
Yeah, there you go.
Alright.
Perfect.
The Allen vector.
Perfect.
Can that be a thing?
An Allen vector?
Yeah.
There's so many people named Alan, I'm sure it's already there.
Are you kidding? Have you
I'm
ever
sure.
met anyone whose name is spelled the way my name is?
Is it A-L-E-N?
No.
Allen.
All right, so Alan's the projection. Now, nothing's perpendicular yet. How are we going to get a perpendicular vector out of this?
Hey.
No,
Let's see.
you're stuck now.
Wow.
You're the projection. How are we going to get a perpendicular vector out of this?
Project the projection onto another projection.
What?
Find the distance.
Here.
Find the distance between U1 and the projection of U1 onto U2. Like the distance between the two, something like that.
You guys understand what he's doing?
Yeah.
So Shem is now what we call as the vector Z, right? What is Z? Z is equal to the projection. So it goes from here to here.
Oh.
So it's who's this vector? U1 minus who's this vector?
Projection.
Alan, the projection. So Z is equal to U1 minus the projection of U1 onto U2. And this is what they call Y hat. You see that?
So Allen is really Y hat.
So Alan is actually Y hat.
Did you spell my name with two L's?
No. Okay? So is that good? All right, now, they all live in a plane. Who wants to be a plane? All right,
That's what I was thinking.
come here, Pedro.
I crashed again.
All right, hold this so that all those vectors are on the plane.
Look at you guys.
Go on the other side.
Well, we can't see them now.
Yup.
So the
You gotta hold it right
so
for
the
the
plane
J.
has to go.
Yeah,
Yeah,
block
hold
the
it for the J.
There you go.
All right, so
It's all coming apart.
What are you doing back there?
maybe can somebody draw them real
Why y'all got a
quick?
screen?
No, it's somebody else.
Okay, fine.
So try to use different colors.
Wait, you might want to scoot it over.
Scoot it over.
Scoot the plane over.
Or do it sideways.
That's the word I'm looking for. Okay, so you're
Landscape.
Your orthogonalness is getting very non-orthogonal.
Yeah, you're getting a little tilty.
Tilty.
You're getting real tilted right now, dude. You gotta take a
I
break.
was like
Tilt.
beginning.
Take a break.
Stop gaming.
Huh?
That's a reference from Home Gaming.
Eh.
I get it, you're too young for the show.
No, I love
Shut up
Home
now.
You get it, you're old, dude. Stop.
This is all on video, guys.
like when you do the right hand rule.
Yeah, you need the sound effects.
I'm
What if
actually
you're a
proud of
lefty?
you for not using sound effects already.
And I think that's why my performance was.
Tapestry.
I would have
So
thrown,
hard.
I would have thrown something at you.
And a projection.
That doesn't surprise me anymore.
True.
I would have shot you with a ballistic.
Can you zoom in and see me doing the like annoyed sarcastic face like on The Office?
Like your Jim or something? Actually, you kind of look like Jim.
Now, can somebody label these vectors?
If this was the opposite.
We called it U1,
Y hat.
Y hat. Can somebody label them? Anybody? Okay.
They're all on the table. They're all on the table by the booth.
Right here, right here.
I found one.
Okay.
This guy. He's still U1, right?
He's U1.
So I can write him as U1.
You should be color coding them.
I should, but I'm not.
It's triggering me.
I'm sorry. This is Y hat.
Okay.
Okay.
Let's change.
So
What
what
do
kind
you
of?
want?
Okay, let's use Y hat.
Are you sure?
Yes.
Go once.
Yeah, go ahead.
Y hat.
What?
This is
Am I a
C.
Are you a what?
A Boeing?
No, you're a W.
Oh, you too.
That's the kind of plane I have.
Please don't for the YouTube. They work very hard as well.
All right. Now, we can have them stay there. Should we have them stay there?
Sure.
Okay. So
Why?
we're good with this stuff right now, right?
This makes sense.
So now, if we just go back to U1 and U2, they form a plane. And we found the projection on this thing, and then we found the perpendicular, okay? Everything that we're doing is still on the plane. So, Pedro's a plane, and he's known as W. He's a subspace of R3. We're in R3, okay? Is that good so far?
Yeah.
So all the W's that you see over there would be Pedro.
I'm Pedro, but
Now, can you describe what W perp is?
perpendicular to W. Or W.
It's the thing moving this way.
So it'll be a plane going this way. So can you tilt a little bit?
If I took too much, I'm in Jay's face.
Okay. All right. So now we can see the plane at a little bit more of an angle,
That's
right?
like a violin. You're the Michael Jackson lead.
So now that we see the plane in a little bit more of an angle, we can introduce another vector. So, well, let's say we don't have a normal vector yet. So we have W right now. W equals the span of U1 and U2. And all these other vectors are on the plane, so I can pick any of them as long as they're not linearly dependent. So if I pick Alan and Jay, they are in the same line, and they will not span all of W. But if I pick Alan and Matt, or Alan and Shem, or Jay and Shem, or any of the other combinations, they're linearly independent, and they can span all of Pedro. Okay? All right.
I'm okay not spanning all of them.
Is that good so far?
Me too, I'm good.
I'm okay with that.
So now,
I'll be out of bounds.
I need a vector V. Can I have a vector V come up, please? All right. Now, Randall is a vector V. He's not on the plane.
So it's
Okay.
perpendicular?
Not necessarily perpendicular. Let's say he's not perpendicular. Okay, so put yourself somewhere.
Oh, he's parallel.
No, we don't want to be parallel. Okay, think about if it's parallel to the plane. What does it mean if it's parallel to the plane?
It means it can be spanned by the other ones, it's just shifted, right?
So that means it can be spanned by the other ones, which means it's actually on the plane. Right? Remember, vectors can move around, so if Randall decided to be parallel, then somebody can just put him on the plane, and then he's on the plane. Right? So let's have Randall be not parallel and not necessarily perpendicular. Okay? So this is Randall now. Let's go this way. So that's Randall, okay? So Randall is V, and Pedro is W. Let's project Randall onto Pedro. Let's project V onto W. Okay? So we need another. Oh, we're out of vectors.
This is still math. No, now we're just tripping you guys.
All right. So
You're all in the same line.
the notation that we use.
Where did you go?
For the projection of V onto W, right? We call that something hat, so we call it V hat. Hat. Right? And V hat is what? Where's V hat? It's on W. So if we project Randall onto W, then it's going to be on W. I need somebody to be V hat.
Brother Gavin.
The honorable
Room.
So many vectors.
So Ali is now V hat. And this, go ahead. So it's a projection of Randall's V onto Pedro's plane onto W, right? And then it's going to be on W. Now, if we take a look at any other vector on W, if we take a look at Matt, if we take a look at Chev, if we take a look at Alan, all those vectors are on W, right? Imagine what's the closest distance to Randall's vector?
Be from Ali.
It would be Ali's vector, it would be V hat. Anything else would be farther away. Does that make sense? That's theorem 11. 10. 9.
Is it?
7, 6, 5, 4, 3, 2, 1.
This one right here. That's approximation theorem. So it says that
1 in 20.
It says that Ali is the best approximation to Randall if we're stuck on Pedro. Okay, so it says that V hat is the best approximation to V if we're only stuck on W.
Why does Allie look like she's Atlas right now, like holding the world?
Okay.
Like,
I feel like you're having a field day. Like, this is
So now,
all the other comments I might have made over the course of the semester.
so now, if I want a vector, if I want W perp, you guys just said it was perpendicular, right? Decided not to be perpendicular. But we can make a perpendicular out of Randall and Pedro, out of V and W. So how are we going to find the W perp?
The distance
Use
between
Ali and
the hat.
to find
Use
the,
Ali.
the distance between Ali and
I
Randall.
don't have any more sticks.
Use your arm.
Yeah, your arm.
Okay. Look, it's not long.
Yeah, to find the distance between Ali and Randall.
So find the vector connecting Ali and Randall. So which one's Ali? Ali's V hat, and then Randall is V. Ali's on W, right? And so the difference between these two. So V hat
This is really uncomfortable.
and V.
Pedro.
So
Now you think it's comfortable, okay?
the difference here minus this is going to be another thing that they call Z. We'll call it Z sub V or something like that. Let's say this is perpendicular. It's perpendicular to W, which means it's in W perp. Okay? All right. Does that make sense now?
Yes.
All right. Thank you. Thanks, guys.
Yeah, I don't think I'll get
Can I click on
Yes,
this?
you did, but
Okay, so for
That was nice.
our next midterm, just remember, W is Pedro.
All right. So I'll take all the sticks and rulers and stuff. And then, thanks.
When you get how to flirt one
Are you a unit?
If you're in a subspace, whatever stays,
Are you a-
whatever happens on a plane
You know what,
stays
we're
on a
gonna-
plane, right?
Unless someone's recording, apparently.
That's like what stop. I hate that. It keeps the right.
So, the key is to get to this orthogonalization process. So this is essentially an algorithm, which, you know, a computer can do. These people get excited.
I'm so excited.
Why did we need that extra vector v to do this?
To go into 3 dimensions.
I mean, well, but didn't we already start off with the 2 u vectors spanning on a plane anyway? Couldn't we have, like, why did we need to do the projections of that guy first?
Oh, because of this. Do you guys understand Alan's question?
No.
So we had, who was the first 2?
It was Matt and Jay.
Everyone get back up there.
Yeah?
So this is Matt and Jay.
Yeah.
They already spanned the plane, right? We didn't really need Alan.
Wow. Wow.
Well, you're a trick question.
You sound just like my mother.
So we have these 2 vectors. They're not perpendicular. They already spanned the plane. So we didn't really need Alan, or who was the perpendicular? Randall. No, he was a perpendicular in 3D.
Shem.
Shem.
Okay.
So we didn't really need those guys. So Alan, remember, was the projection, and Shem was that perpendicular on this. So we didn't really need them because they already spanned the whole plane. They already spanned Pedro. So to find a perpendicular for this, you could just take these 2 vectors. So why did we bother with Alan and Shem? Well, because of this. What we're going to do is, if we have 3 random vectors, any 3 random vectors, what we're interested in doing is to orthogonalize the 3 vectors that span the same space. Okay, so that means we needed perpendicular vectors on the plane. So we needed Alan and Shem to make the perpendicular vectors, and then so it would be Matt, Shem. He was here, but we can move him over here. And then who was the last perpendicular vector? Oh, so Ali was the projection, but she also became the perpendicular vector. So now I have this, and this that are all orthogonal to each other. And that's what this Gram-Schmidt process is. Yeah?
So it's merely, the Gram-Schmidt process is merely a way to orthogonalize the vector so we can actually find an orthogonal vector.
Yeah. So if you have any number of vectors, you can have just 2 of them, and then that would be simple. If you have 3 of them, it takes a little bit more work. And if you have 4 or 5 in R4 or R5, then it'll take more work. But the process is still an algorithm. So what is the algorithm? So the theorem says that if you have a basis for a subspace, it could be the whole space, or it could just be a smaller subspace. But we're talking about R7 or something like that, and then we have a 4-dimensional space in R7, and we're looking at 4D. But if you have a given basis in the subspace W and Rn, then you can, this is your original set of vectors, x1, x2, x3, x4, whatever. And then you start off with one vector, and we'll just use that same vector. Now, if I project this vector, or my new vector, if I project x2 onto V1, then this fraction with a V1 is the projection, and then when you subtract it, it becomes that z vector that's perpendicular. Right? So who was it? So this is Matt in the beginning. This is the projection, so this is Alan. And this is x2. x2 was J. And we subtracted them, and we got Shem. So Shem now is V2. Okay? So to go to the third level, x3 was Randall. So these two combined over here is going to be Randall projecting onto W, projecting onto Pedro. And these two put together would be Allie. And then now, if you take that up, you subtract this out, Randall minus Allie is the second Allie, when she became perpendicular to the plane. So those three vectors, who are those three vectors? Starting off with Matt, the original vector, Shem, after we do the subtraction, and Allie, after we subtract her from Randall.
Wait, Allie 1 or Allie 2?
Allie 2. So this here, if you factor out the negative sign, this here would be Allie 1, who's on the plane. And then you subtract them, and then it becomes perpendicular to the plane. So this is in R3, and that's as far as we can visualize. But this thing can extend to any Rn. If you have more vectors, then this is what you would continue on doing. So then you have V1, V2, V3. Those three vectors are all perpendicular to each other. Random.
So I'm the x3, right? The thing.
You are x3, yeah.
All right, so it's like that, the v minus v on the board. That's what you're explaining.
No, I guess in that, on the board, you
Yeah.
were V.
Yes.
And then Allie was V hat on the plane, and then when you subtract you two, then it becomes Allie when she became perpendicular.
So the v3 is the z right there.
Yes,
Okay.
Which one was Chef?
Shem was V2.
Then who's X2?
J.
X2 was J.
And who is X1?
Matt.
But I thought Matt was V1.
X1 is equal to V1.
Oh, never mind. Sorry. Thank you.
So that's the first thing, is that we're going to just let the first vector be whatever the first vector is, and then we'll adjust all the other vectors after that.
I thought that made me V2.
What?
I thought that made me V2.
You are this without being subtracted. So you are this
You're the
vector right here.
projection.
You're the projection.
I don't even get a name.
Where's
You're-
the Allie
you're like-
vector?
Isn't that X hat? X2 hat?
Okay.
X, we could call it x2 hat, yeah.
I'm
And then
labeling
this,
these all
again, with the
names.
minus signs factored out, so we can actually look at this thing. So if we just look at this is Allie on the plane, and then when you subtract Randall minus Allie, and then this is Allie perpendicular.
You're basically removing the plane that you previously.
We're not removing, but we're projecting onto that plane. So we create a plane out of the vectors, and then this is what you have, the projection onto that plane. Okay? So now, if we want to go one more dimension, let's say we all lived in R4, we have an R3 subspace, a subspace that's three-dimensional, and then we have a fourth vector that we want to project onto our space, then we just continue on the process. Okay? Does that make sense? Yeah.
So we're just taking a series of projections.
Yeah, we're just taking a series of projections.
And for in the V3 equals x3 minus all that business. So the x3 times v2 would be the projection of 2 onto x3.
X3, well, it's X3 minus this whole thing. Yeah, so it's X3 minus the projection of X3 onto some space that we created from the first two.
Okay.
Okay?
How do we remember the order in which this happens?
Well, let's see. If you just look at it, whatever X you're dealing with is going to be part of the dot product in the numerator. The denominator's dot product is a dot product with a vector with itself. What's that vector? That vector is really that just vector that you're multiplying with, right? And you're just going from V1, from V2 to V3. And then if you look at the general term, it's going to be, this is the new vector XP. That's your new vector that's not projected yet. You've so far created a space, an orthogonal space, or a space with orthogonal vectors V1, V2, all the way to VP minus 1. You've created that subspace, and now you want to project VP onto that subspace. And so to project that, you kind of ignore this for now, and then you do the projection of VP onto this, and then you subtract, and then you get a new vector that's perpendicular.
So essentially, VP, you're just taking projections from, so it's from this projection of all those vectors on VP, or
It's VP being projected onto the space that's spanned by all these other vectors.
okay. So we're kind of orienting.
Making what?
Never mind, I'm not making.
Okay, so going back to our people that were vectors, we start off with Matt and Jay. They weren't perpendicular, but we created a perpendicular vector, Shem. So now Matt and Shem are perpendicular and they span a plane. So that plane, Pedro was that plane, and now we have Randall coming in, and we want to project Randall onto that plane. And so we found Allie's vector, and then we subtracted them two, and then we found Allie's second vector that's perpendicular. So now Matt, Shem, and Allie's second vector are all perpendicular to each other. All of them perpendicular to each other, which is really a little bit more interesting than just two of them being perpendicular. All three of them are perpendicular. Now, if we want to extend this, we can get a fourth vector if we were in R4, and then that would be perpendicular to the other four vectors, or the other three vectors that we have.
So hard to picture.
Because you can't picture it. It's hard to picture because you can't picture R4. But in R3, at least, with those three vectors, you got a picture of them, right? So, so these are orthogonal bases, and if for some reason we want an actual orthonormal basis, what do we have to do?
Divide by its magnitude.
We just normalize every single one, and then we have an orthonormal frame. Okay?
Have an example of this.
So do we want to do an example in R2, R3, R4? R3. Just go in R3, all right? So let's do an example. Gram-Schmidt process.
Computer do it.
here's our example. We have these three vectors in R3, and we want to construct an orthonormal basis that's the same as these three vectors, well, kind of like the same. So let's label them, just for the sake of being consistent with the theorem, let's label them x1, x2, and x3. So my new vectors, I'm going to call them v. My new vectors are going to be orthogonal to each other, and I'll start with v1, which is equal to x1. Well, that was easy. So v1 is equal to minus 1, 2, minus 2. Now I want to get another vector that's perpendicular to this one, that's going in the same direction as x2. So according to the formula, v2 is going to be equal to x2 minus x2 dotted with v2 divided by v2 dotted with v2 times v2. No, sorry. Should be v1, right? And then times v1. So the dot product is going to be positive 1, 0, positive 2, so that's 3 divided by 1 squared plus 0 plus 1 squared. And so this is going to be v2. Ugh. Something wrong? Oh yeah, subtract x2 from it. So this whole thing, v2 is going to be x2 minus this whole thing over here. So x2, what was x2? x2 was minus 1, 0, 1, and then now we just got minus negative 3 halves, 3. Got fractions here. Minus, minus, plus. So this is positive 1/2, negative 3. This is a negative 1, right? Positive 2. Is that right? Did I do that right? Yeah.
Wait, how does for the 3/2, the denominator shoot? How'd you get that?
Oh, I got it from this divided by this.
Is that
I got
9?
v1 dot v1 is 9.
9? Oh, sorry. All right.
It's all wrong, isn't it?
It's all wrong.
It's okay, so is mine.
All right, let's do it again carefully. And I forgot that x, blah, blah, blah. All right, so v2 is going to equal to x2 minus x2 dotted with v1 divided by v1 dotted with v1 multiplied with v1. So x2 is minus 1, 0, minus 1 minus, now this is where the fraction comes in. The dot, was the dot product of the first one correct?
Yes.
3. And then the dot product of v1 dotted with v1, I dotted v2 over x2. So 1, 4, 5, 4, 9. And then this is being multiplied by v1, minus 1, 2, so minus 1, 0, minus 1, minus, this is 1/3, right? Negative 1/3, 2/3, negative 2/3. So V1 minus positive, so that's positive negative 2/3 and negative 2/3 and negative 1/3. So that's V2. Is it? No?
No, it's
So, does this work?
yeah.
Okay, good. So,
Wait,
so that, what?
x2 dot v1 is 3?
I hope so.
I,
Yeah.
yeah? That's
Negative 1
wait,
plus negative 1 is 1 plus negative 2
0.
is negative 1.
Oh, that's a negative 1. I have it written as positive, that's the problem. Yep. Never mind, you're good.
Okay. So I got V1 and V2. Now to find V3, I would just use this formula. So V3 is going to be equal to X3 minus X3 dotted with V1, V1 dotted with V1 times V1 minus X3 V2 dotted with X3 dotted with V2, V2 dotted with V2 times V2. Now, before I go on, I'm just looking ahead a little bit at V2, which is a fraction, or a bunch of fractions, the vector full of fractions, right? Now, does it matter what the length of V2 is? Let's think about that. We found V2. Who is V2? So Matt was the first one, and Jay was the second one, but then we projected Jay onto, projected Matt onto Jay, and we got Alan, and then we subtracted, so Shem is the second one. So Matt and Shem were perpendicular to each other on the plane W, right? The question is, does it really matter what the length of any of those vectors are, even if you're on W?
No, as long as you're on the plane.
As long as you're on the plane, right? And as long as you're perpendicular. So as long as you're on the plane, and as long as you're perpendicular, then size doesn't matter. So just scale it so that it is we're dealing with nice numbers. So what if we call, instead of V2, why don't we call it V2 star equal to the scaled version of V2 so that there's no fractions. We'll call it -2, -2, -1. I just multiplied everything by 3. Okay? So we scaled it. So now, instead of dealing with V2 with fractions, we're dealing with a nicer V2 that's still on the plane and it's still perpendicular to the first one. So why don't we adjust this formula so that we're going to be dealing with a nicer V2. Is that okay? All right, so let's do this. X3 is -2, 1, -1. And then we have X3 dotted with V1. So that's the same thing as X1. +2, +2, that's 4, plus 2. I got 6. And then V1 dotted with V1, we did that already, that was 9. And V1 was -1, 2, -2. Now this is where our scaling pays off, we scale so that we don't have any fractions in our formula, then we're just dealing with V2 star instead of V2. So V2 star is -2, -2, and 1. That's easier to dot than -2/3, -2/3, -1/3. So we want to dot that with x3. So that is going to be +4 minus 2 plus 1. So it's 3. And then V2 dotted with itself, V2 star dotted with itself, 4, 4, 1 is 9, right? And then we use -2, -2, -1. So what do we have? We have -2, 1, -1. This is 2/3 minus 2/3 -2/3 plus 2/3. I'm getting mixed up now. 4/3 minus, and then this is positive 4/3. And everything here is going to be positive, so it's 6/9, 6/9. Oops, let's reduce that. So 2/3, 2/3, 1/3.
We have a question for the second one. Why is the second one negative and the third one positive? Shouldn't it be the other way around?
I distributed this also. So and then made this into a positive.
Oh, sorry.
Well, that wasn't very clear. Anyways. 4/3 minus 2, -2/3. 4/3.
Minus 6/3 and minus 2.
And then -2 in the bottom. Okay. Well. Let's hope that this is correct.
I think the second number is 1/3.
Instead of 4/3?
Yeah.
Agreed?
Yeah, I got 1/3. So that's 2/3 on the bottom. Positive 2/3. Is yours positive?
Yeah.
All right, well, let's see. So we start off with -1, 2, -2. I don't know if I have enough time to do this. -1, 0, -1. So these are the three vectors that we start off with. They're not at all perpendicular, right? So now, we're going to come up with 3 new vectors. Well, one of them is the same, exactly the same as the other one.
Whoa!
Right? So that's one vector.
Thick. Huge ices.
Triple C.
Oh,
It's just an arrow.
So the other one was our V star. We just V2 or V2 star. What was it? -2, -2, -1. perpendicular, yeah?
Yeah.
Very 90 degrees.
And then our last one, we can even change the size again so that we can go -2, +1, +2. That's a 2, right?
Yeah. Let's see if we were right.
I got 2/3. Oh, yeah.
Let's see if we were right. Hey!
Oh, different colors.
Look how pretty that is.
So that looks pretty perpendicular.
Oh, yeah.
Now, if you want an orthonormal basis, you just shrink it down so that it's all unit vectors.
So you just normalize those vectors that you just
Normalize
have.
those vectors, yeah.
And why?
So why would you want to normalize the vector?
I have a broader question on that topic.
Orthonormal basis.
Hold on.
Why are we doing this at all?
Yeah.
Because if we started out with a basis for R whatever, and we wanted to find another basis for it that was orthonormal, couldn't we just make it 1 0 0 0 0 1 0?
Okay, well, imagine you're flying in a spaceship in space, right? You have a velocity and you have some sort of acceleration, and then you're moving around, so you have an up direction. So you have these three vectors, the velocity and acceleration may not be perpendicular to each other. And you're flying along, and then you're up direction. You're flying along, and then you want to hit a target. So if I know my coordinate vectors look going this way, I have to try to find a way to get to that target using these coordinate vectors, and that's going to be kind of difficult. Usually, if you have an orthonormal basis, that they're all perpendicular, they're all unit length, then it's easier to get to that point. And so what we could do is with that velocity vector, this could be your first vector v1 or x1 or whatever, and then your acceleration vector could be your other vector. You make an orthogonal basis between these two that's going to be on the velocity and acceleration plane, and then you find a third vector and make it orthogonal. And then now, if you have everything of unit length, then getting to your target would be easier to get, easier to shoot. Okay? So if you're doing computer graphics and you're doing gaming, and then you're floating around in space, then this might be important to find an orthonormal basis. Now, of course, calculators and computers can do that really quickly, but you're going to do it by hand as a worksheet. Okay, so your worksheet will be online. You will be in a spaceship, and you will try to hit a target by doing an orthogonal basis.